Okay, so we're here today just to give a quick presentation on the MSc in Electronic and Computer Technology and the MEng program, the Masters in Electronic and Computer Engineering program at DCU. And we're focused, this is June 2026, so we're focused really on the September 2026 entry, but we will point out that there is a second entry into these programs in January 2027. So if you happen to miss the entry point in September 26th because of visas or getting your documentation in order, there is an entry point in January 2027. Okay, so we'll go through them like that. So the first program I'm going to talk about is the MSc in Electronic and Computer Technology, and Richard is going to talk about the MEng program. So I'm going to hand over to him after about 20 minutes. So I'll do the introduction to the university and talk about the differences between the programs. So DCU, Dublin City University, I'll show you where it is on the map soon, but it's a relatively young university. It's always in the top ranked universities in the world, and when you're in the top rankings, it's important to remember you've been ranked out of about 25,000 universities. So there's a lot of universities in the world, and to be in the top few hundred is exceptional. We are always ranked as one of the young universities. We're very, very high on graduate employment. So we're 19th in the world when you consider that's 19 out of a very big number for graduate employment rate in the university. And that's helped because of the practical nature of our programs and because of the sort of strong economic environment and hiring environment in Ireland, which I'll talk about in a second. We're routinely ranked in Sunday Times rankings and other rankings, and we're recognised internationally for global and social economic impact. So we the rankings are never perfect; they're never a perfect rankings, and but we always achieve well in those rankings. Our location is perfect, and you'll see we're Ireland is a small country of about 5 million people. Dublin is a relatively small city. It's our capital city, but it's still a small city of about 1.5 million people. DCU is positioned between the airport and the city centre, so you're not looking at a big distance here. We're just a few kilometres away from the airport and a few kilometres away from the city centre. But what you will notice here is a lot of brands that you recognize. You'll see companies from everything from in the center of the city, from Google to Stripe to out to IBM, out to Intel, Adobe, Xilinx or AMD, Amazon on the south side of the city, Vodafone. All of these companies are companies that hire our graduates, and that they're only the kind of the brands that people would recognize. Obviously, there's a lot of other companies, particularly in the embedded space, that would be less obvious. They would be inside the products rather than on the outside of the products. So we have a lot of different companies that are in our space, even within the Dublin region, that employ our students, which helps with our graduate employment rate. So really, Dublin is the Silicon Docks home to a lot of different companies like Google, Microsoft, and Amazon. We also have research centres within the university, DCU, Trinity, and UCD. We share across those in areas like Insight for data analytics and Connect, and these are going to be formed into new research centres in the coming years. We have a lot of engineering students are placed in tech, in sort of in the software engineering side, the IC design engineering side, but also we're seeing increasing numbers of students placed in pharmaceutical and medical devices where there's needs for engineering capabilities in smart manufacturing, in robotics, in physical AI, in medical device technology, embedded technology. And so that's an important area as well as the sort of more traditional semiconductor engineering that you see with Intel and AMD and Xilinx. And there's also robust startup environments, and right beside DCU we have DCU Alpha, which has a lot of startup companies attached to it as well. And they're in everything from edge AI to fintech, and other AI applications, including autonomous navigation. So Ireland, just to explain, is a sort of a technology hub for Europe, the Silicon Valley of Europe, if you like. And given the size of the country, it's not much different than the actual area of Silicon Valley in California. So we'll take that title. So that's the environment for recruitment. Outside of that, we've got then the school that we're both in, and that you will be studying in. And the school is the School of Electronic Engineering. Now, the School of Electronic Engineering is a traditional title. It's been on our school since the 1980s. Our programs are typically in the electronic and computer engineering space, and we're spread across two buildings. The engineering building where our offices are, this is the Stokes building, and that has purpose-built laboratories and teaching rooms. And we have a new building, which is our Polaris building, which has purpose-built research laboratories, teaching laboratories, and new lecture theatres as well. So our engineering school is split across these two sort of state-of-the-art buildings within the campus. They're only right next to each other on the campus, so you don't have far to walk to go from one to the other. Within our school, we have about 24 academics, professors, and we have, as I said, modern teaching laboratories, teaching rooms. And very importantly, all of the modules we deliver on these programs are research-led. So, for example, my research area is in Edge AI and embedded devices, and that then features in the modules that I teach on the program in connected embedded systems and Edge programming with C++ and Rust. So that research is reflected in our teaching, which is important because it means that everything is current and up to date. It's also industrially relevant because we reach in, DCU is very closely aligned with industry, and we have an industrial advisory board, and we talk to our industrial advisory board about the skills that students need now and into the future. So that then features into our modules as well. So everything is industrially relevant in terms of what you study. So when you're preparing your CV at the end, you're presenting tool sets and tool chains and skills and that are important to employers in our space. So I said earlier, I'm going to talk about two programs, the MSc and the MEng, and I'm going to use just those titles. So I'm going to focus on the MSc, and Richard is going to talk about the MEng. So these are the codes that you use when you make an application. So this is a little bit confusing. We know from the questions that we get asked, what's the difference? And the simplest way of explaining it is to say that the MEng, what Richard is presenting, is hardware-led. It's end-to-end engineering focus. So it's from low-level devices and circuits through to embedded systems and into communications and the broader technology. Whereas the MSc is more software-led. It's more computing aligned, and it's intended for students that want a deeper software capability and want to work in areas like edge devices and higher level computing systems. And I would say what's important there is architectures and compute is really important there as part of that. So these are the way that these two programs are split down. This is the MEng that Richard will talk about, and this is the MSc that I'm talking about. Within the MSc, we've got two majors, a major in IoT systems and a major in edge and IoT security. So I'll talk about those two. So really, we often refer to this MSc as the MSc in IoT, and you can see why. Richard will talk about the MEng, which has physical AI for future robotics, IoT devices from low-level devices to IoT, so a little bit distinctive from the IoT systems, which is more software-oriented, data network telecommunications, photonic systems, low-level lasers and optical systems, and then semiconductor engineering and IC design, so very low-level hardware design. So you can see there's quite a difference. Hardware-led on the left, Richard, software-led on the right with me. Okay. So that's important. And software means different things. It's not like Python software. Software is everything from firmware right up to high levels, from firmware and edge programming, efficient programming on edge devices, to network programming, to full AI implemented on cloud solutions. So that's what software means. It's a full spectrum software rather than a software engineering. So the MSc is focused on the Internet of Things, and the Internet of Things is an important concept. It relates to the sort of next evolution of the Internet, a change in the way in which we gather and distribute data. So we know what the Internet is today in terms of the social Internet of Instagram and Facebook and Reddit and X and all those systems that allow humans to communicate to each other, and that's the sort of latest, the sort of human evolution social network. The next network that we're developing now, and it's only in its infancy, despite the fact that we've been talking about the IoT for some time, we're only in the first phase of the Internet of Things. So the first phase of the Internet of Things is devices talking to devices, and ideally without a human in the loop. So that allows the internet to reach out and talk to sensors, to sense the real world, and also to reach out to actuators and motors to influence the way that the real world is appearing. So, you know, that's the sort of connection to the internet is what we're looking at. The first evolution was where we talked about loads and loads of different sensors all talking to a single server in the cloud to develop things like smart traffic and applications like that. But the next generation of IoT that we're focused on, I suppose, in this program is where we're able to make decisions at the edge of the network. So we talk about this as edge IoT or AIoT or artificial intelligence of things, where we're connecting AI devices directly to edge devices. And that's important. So for example, if you think about something like, and I'll give you an abstract example, something like a smart vehicle that detects pedestrians and applies the brakes if there's a pedestrian in front of the car or the scooter or whatever type of device it is, it's not possible to be sending video data to a cloud server in California, processing the data in a cloud server in California, detecting the person, and then sending a signal to apply the brakes. The latency or delay that would encourage, or the processing delay, means that you'd long since have driven over the person, over the pedestrian, before you realized there was a pedestrian present. So it's very important in the next generation of IoT devices that we start to take decisions at the edge of the network, and we make decisions very quickly with low latency and quick feedback. But to do that is quite complex because we're talking about very, very complex computing devices that are needed to make edge inference decisions at the edge of the network. And that's really where we're focused on. We still need to sort of centrally manage those devices, update firmware, secure those devices. So it's very important that we still have the management layer of the internet, but we have to be able to make decisions at the edge of the network. So we're focused on all of those elements, and you can see that obviously the major insecurity is critical because we need a way to secure all these communications. So that's the area that we're working on. Whenever you hear the word smart related to technology, smart traffic, smart internet, smart grids, smart wearables, smart home, smart health, you're talking about IoT devices. You're talking about some sort of data collection reaching out to the real world from the internet or vice versa. So we originally designed this program in collaboration with industry. We work with industry partners and we identified the critical skills that are important to students. And that's how we ended up with a sort of a real and focused and practical IoT program. As I said, we apply our research to what we build, and we've also got projects that are built around our modules, and we also have flexible delivery modules. I'll talk a little bit about that more in a minute. So I'm going to focus on the majors. So in order to complete these programs, whether it's Richard's MECE or my MCTY, we have a very similar structure. Students have to do 4 modules. If you want to do a major, you must do at least 4 modules related to the major, plus project elements related to the major, plus then you have free choice of other modules that you can choose. And that's the general structure across all the programs. So when I talk about this, the MSc with a major, we're talking about 4 core modules related to the major, 4 optional modules, and then the project attached to the major as well. So we'll talk about that shortly. So we have 2 majors on this program, the major in IoT systems, and this is where where a student will have covered the entirety of the full stack of IoT. They'll have real practical skills about how they can connect smart edge devices, connect them through data analytics, and do important processing with those. So that's the major in IoT systems. The major in IoT security is focused on the network edge security, looking at how do you protect critical infrastructure, and deals with cryptography and wireless security. And I'll show you some of the modules in a minute that relate to those. So the major in IoT systems, and just to show you the core modules, you can do any 4 of these modules. So you have a choice of 5 modules. You can pick any 4. Connected embedded systems is about how do we connect these sensors that I talked about to the network. So that will be connecting sensors to each other, but also connecting sensors to the real world. And that covers everything from embedded Linux to how do you connect to real world sensors. Security for IoT and edge networks, critical for any IoT system that you're aware of the security gaps. And because of the complexity of IoT networks, they have a very wide attack surface, right from the sensors right through to the firmware updates to the cloud elements of the system. So security is a very challenging, and I would say even more challenging than in traditional desktop computing. Real-time digital signal processing is about how do you connect the sensors and do that in a real-time way. Data analysis and machine learning is a follow-on module, a more complex module that looks at extensions of content in the first module, and looks at how we can do everything related to machine learning for edge devices, including concepts like federated learning. And finally, you have the choice of network stack implementation, which is about how the network actually works for IoT devices. Along with these 4 modules, we encourage students to pick 4 of these modules, and they include Data Analysis and Machine Learning 1, which is obviously critical to Data Analysis and Machine Learning 2. Edge Programming and with C++ and Rust, a very practical embedded module that ties into connected embedded. Wireless and Mobile Communications, which ties into network communications. Mathematical techniques and problem solving, which is a general purpose module for students that maybe are coming from a computing background that want to make sure they have the fundamental engineering math skills. And finally, bioelectronics for wearable IoT devices. So you can see how these tie together. I've left the slides here and I won't read through it, but then you also do a project that's 30 credits related to this area. So roughly 30 credits of core modules, 30 credits of optional modules, and 30 credits related to the project, giving you 90 credits in total. The major in edge network security, I won't spend as much time on this, very similar, but focused absolutely on network security. So the core modules are connected embedded systems, security for IoT and edge networks, network security, which is a computing module that ties into the program, and a new module on physical layer principles for security communications. So the full stack. So if you know anything about the OSI stack, the important area that you have to secure in IoT devices is the physical layer, and that's a new module that's been built against this program. Along with that, we recommend that you take these modules as well. So the focus is on securing next generation edge and IoT networks. And again, 30 credits of core, 30 credits of recommended, and 30 credits related to the project. So again, for MCTY, and this is pretty much the same for MECE, this is the program structure. So typically students must complete, I should say, not typically. Students must complete 8 modules plus the project modules as well. So this is the 4 plus 4, it's the 30 credits, the 60 credits here, and the 30 credits. So it's 90 credits in total. And just for your own calculations, if you're going through this trying to work out the workload, each 1 credit roughly equals 25 hours of study. So you can see that when you multiply 90 by 25, it's a big number. That's the amount of interaction you're expected to have with the program over the period of the program. Now, if you enter in September, you are able to complete this program in 12 months. Now, if you did an undergraduate degree and you did 2 semesters and you had the summer free, that's what we would call a normal academic year. This is a very full packed 12 months. So this is 12 full months. This is not where you have the summer off, okay? So on MCTY and MECE, if you start in September, we would expect that you have 12 weeks of study between September and December to complete your 4 modules plus your exams. That's what we typically require the students do. So 4 modules between September and December, and then you start the next semester, semester 2 in January. You do 4 modules, 4 taught modules. That means you've got done 8 taught modules in total, plus what we call the RD&I, the Research Training and Project Planning module, EEN 1101, which is 7.5 credits of your project. And that helps you build the fundamental skills in project managing, project planning and management related to the project. And by the time we get to May, you will have a project plan in place and you'll be working with your supervisor to build your project structure so that you are ready to go in your project during the summer. And then the third semester, which is a little bit of a contradiction in terms, we don't talk about trimesters, but we talk about semesters, and we have 3 semesters here in a single 12-month period. So then between May and the end of August, you complete your project. So you roughly have 3 months to work on your project over the summer. And this is the EEN 1095 project. This is 22.5 credits. This is you're expected to build a capstone project that covers the content that you've seen in your modules over the first 2 semesters, and then that's you're interviewed on that at the end of August. So in theory, you come in September. Well, ideally you come in September and you're finished then at the start of September of the following year. So we squeeze it all into 12 months. It's hard work, it's difficult, it's a challenging program, and you're looking at roughly 10 hours per week for each module that you study. So 40 hours per week is roughly your workload in each semester. So it's a challenging program. It's very much a full-time program, and we are squeezing. It's a full master's. If you're looking at master's programs in other parts of Europe, you'll typically see a 2-year master's program. We're squeezing it into 12 months, but that's because we're squeezing in a 3rd semester. If you don't, if you're not ready for September entry and you are entering in January, this is the structure that we would have in place for January entry. You still must do the exact same program elements. We typically ask the students do 3 modules in their first semester, which runs from January to April. They have the summer free, and under the visa agreements, if you're an international student and you're coming to Ireland, you're entitled to work 40 hours per week during this period between April and September. And then we recommend the students do 3 modules in autumn, and then finally 2 modules, so that gives 3 plus 3 plus 2 is 8 as before, plus the training, plus the project then during the summer of the following year. So it takes roughly, we call this a year and a half or 18 months, but really it's closer to 20 months of period, but not all of it is spent working on the program. So that's the program structure. If you do this over 20 months, it's a little bit lighter if you come in January because you're doing 3 and 3 rather than the previous structure, which is 4 and 4. So there's a little bit more space for you to work through the content. So that's January entry. Clearly it takes longer, but a little bit lighter workload. It's the same program fee whether you come in September over 12 months or whether you come in spring over 20 months. It's the same fee in both cases. Eligibility for this program and indeed for the MEng program, we expect that students will have achieved a H22 or GPA 2.5 in a level 8 primary degree in computing or engineering or an equivalent cognate discipline like physics, for example. So that's what we expect as an entry point. The international office, if you're applying as an international student, clearly we can't really give you feedback in terms of the equivalency, but they do a NARIC equivalency when they do when you make an application, and then we work out if or the international office work or the DCU Global works out if it's a cognate degree or if you're suitable for admission. For part-time students, for students in Ireland, this does not apply to international. It does not make you eligible for an international visa. Part-time students are there is a part-time offering available, but it's only for it does not qualify for international study visa. So that's really it. I'm about to hand over to Richard. Just leave my email address there on the screen, and you can just Google me, Derek Malloy at DCU, and you'll find my email address. And I'm happy to take any questions that you might have at any stage, and I'll help you with the academic side. For admission information or issues related to your documentation, it's best if you go through DCU Global, through the DCU page that you have, through the contacted details you get when you're making an application to DC 877. They will respond very quickly. There's a team of people to help you with the admissions, but Richard and I are focused on the academic questions that you might have, things around which modules might you register for, things like that. That's what we are best able to help. Or if you have specific questions about the content, we can help with that. So I'm gonna stop share. Richard, you might have to request share, so I can, or stop share here. I can stop it here.
I
Richard,
think
I'll hand
I
over
can
to
do
you
it
now.
this way. So
Yeah.
thank you. Thanks, Derek. Richard Bulger here. So I'm in charge of the MEC engineering program, which is the sister program for the MCTY. A lot of these slides will be very similar, so I'll skip over the ones that have been already presented. Let me go in and see where we are. Right. Ooh. Cut my head off. There we go. Um, So it's the same slide here as our two buildings, Stokes building on the left and the Future Technologies Polaris building on the right there. I'll do a little fly around at the end of this if we have time, just to show you where all the important buildings are on the campus. So Dublin, if you don't know us, we're the capital city in Ireland. Population of the whole country is 5.4 million, and we've been in the EU since 73. We use the euro currency. Languages, Irish and English. Everybody speaks English, so you don't need to worry. All the lectures would be in English. You do need to worry that we drive on the left, so that might be an issue for people who drive on the right. Be careful crossing roads, please. This is the same slide. Derek explained that we have an awful large array of international companies who are either based here or indeed have their EMEA or European bases headquarters here. So employment is quite good for people who graduate from the program without having to travel vast distances. It's a colourful enough campus. We do have, I think, 5 campuses. The main one is the Glasnevin one, and that's where all your work will be done. So you do have access to the libraries on the other campuses, and we can show you where they are. But everything you need is in DCU Glasnevin. There's the same building, Stokes building. Derek and myself are on the 3rd floor of that building. The labs are in the basement and on the 1st floor, and on the 2nd floor, some lecture rooms. So you'll spend a lot of your time in this building. The MEng or MECE program, it's the longest running of its type in the country. We're going over 20 years now. And again, it's the same structure as previously explained. Most people start in September. They do 4 modules. Then after December, they do 4 more modules, and then they do their project over the summer. There's same as MCTY, there is a January intake, but that's over 18 months or 20 months really. So, but at a lower pace. So you do 3, 2 modules. So as explained in the previous slides. So the difference between the engineering and the CTY is mainly we're at the lower level. We're more hands-on with the physical world than the airy-fairy computing higher levels of the OSI model. And we've got five distinct majors available. I'll go through them in details with what modules you need to take for core and then recommended. And but just to give you an overview of how they are different from each other. The first one there is major in physical AI. So AI is huge at the moment. Most people have used chatbots. We've got something here called physical AI, which is instead of talking to a piece of software, the software actually interacts with the physical world through either robotics or from Internet of Things devices out there or sensors. It could be cameras. So it's anything that where AI interacts with the real physical world. And in alliance with that, we've got a concept called digital twins. So a digital twin is where you previously you might have a computer simulation of some like the weather system or traffic in a city. But bringing that one step further, if you integrate that with real-time sensors, like could be temperature, pressure, could be traffic loads on different streets. For example, Formula One, you might have a race in a racing car, one side of the planet, but the data from all the sensors, and there might be thousands of sensors on a car, that will go into a digital twin in the factory, and they'll get the driver's input and steering and acceleration, and they'll work out if any part of the car is going to break because of the way the driver is driving. And it's really impacted motorsport, for example. So now cars rarely break down. If they do, it's usually due to the driver not taking the warnings from the headquarters where the AI is telling it really what to do. So that's the feeling for the physical AI major. We have the major IoT devices, which is very similar to what Derek talked about, but again, it's more on the physical world side of things. So we talk about how do you get power for an IoT device? The whole sort of premise of this, when computers first came out, they were very big, and then with integrated circuits, they shrunk down, and this it goes either they become more powerful, the chips, or else they get smaller and more lean and efficient. And you can have very small devices now, which are capable of doing as much as a mainframe could do in the 70s. That leads to ubiquity in computing platforms everywhere. So there's more microprocessors on Earth than humans by a factor of 10, I think, at this stage. And they make a lot of them every day. So that in turn brings its own issues in terms of securing them, getting information to them from them. They might be out in the field where there's very little power. They might only come on once there's temperature there that they can harvest. Uh, and then they can switch on, talk back to home, or receive instructions. That's the sort of thing we do in the IoT devices. The photonic systems, so we are electronic engineering. Electronics is about managing and controlling electrons, the smallest electronic particle. Photonics is about the control of light particles, photons. And to that end, we'll talk about lasers and fiber optic communication systems. And also in terms of integrating with electronics that in modern data centers now, a lot of the computers all have to talk to each other at the highest possible bandwidth with the lowest latency. And the only way to really do that is through fiber optic connections or laser connections. And that shrinks down to now where you have electronic processors. You might have multiple cores, but the bandwidth between the cores is limited with electronic means. So we're investigating stuff like using light photons, which gives us better bandwidth and more powerful systems. So that's what we do in the photonics major. The data telecommunications major is about really how the internet works. You do subjects like switching and routing protocols. Because it's sort of grown organically since the early days of the internet back in the late 60s. And it's a lot of protocols all dumped on one another, and a lot of it doesn't make sense because historically we did things this way and that. So it's a hodgepodge of different protocols. They've tried to tighten it up and simplify it and make it standard as much as possible. So you have stuff like IPv6, MPLS, that was sort of network protocols that help us achieve the scalability that the internet has now. So you can type on a small screen in Ireland and then control a device in Hawaii as if it was beside you. So it's quite a lot of engineering to be able to get those packets from A to B and back. And finally, we have a major in semiconductor engineering, integrated circuit design. This is really down at the physical hardware layers. So you'll do actual chip design, both analog and digital. They're similar, but they're very different skill sets. So digital stuff can be very noisy. And then if you want to do an analog chip, the last thing you want in an analog chip is noise. Think of your hi-fi system, audio, digital circuit switching cause a lot of problems. So if you've got mixed analog digital chips, there's a hell of a lot of design protocol that you have to take into account. So we do stuff like that in the semiconductor engineering. So these are the core modules. So here on the left, we've got four core modules in the physical AI. So we've got embedded systems, computer vision, obviously, and then we've got data analysis and machine learning, which is really the core of where machine learning and AI is at the moment. There's been a bit of a revolution now with the advent of transformers from Google. And then we've also got real-time digital signal processing. So the computer will be able to take signals in from the world, but it needs to be able to understand them. So this is where DSP comes in, and you do harmonic analysis and frequency analysis and Laplace transforms and stuff. They're the required, you must complete those four. On the right, then we've got the recommended ones. They're optional, we call them, or recommended. For example, data analysis and machine learning 1, we strongly recommend that you do that. You do machine learning 2, which is required. Interface technologies, image processing analysis, and edge programming. The IoT, very similar. We've got a bit more hardware modules than the required. You have to take 4 of those required ones. You've got CMOS analog design as an option, or as a recommended core one. And then you've got machine learning again, embedded systems, DSP. And you've also got network stack implementation because the networking is essential for the IoT space. On the right-hand side, we've got the programming module, wireless communication again, and then data analytics 1, and then bioelectronics, which is all about interfacing with biological systems, whether human or animal or bacteria, or there's a lot of research going on in how we could communicate with organic material using proton. So some electrons and photons, so then we were moving on to proton communication, which is quite slow, but very, it's what the brain uses. Our photonic systems, there's 4 core ones there. I mentioned photonic devices, nanoelectronics, semiconductor device manufacturing, and photonics. You also need to pick 4 optional ones. The one we have listed there is solid-state electronics and semiconductor devices. There is about 35 modules that you can pick from. And again, as Derek said, if you need advice on which ones to pick, you can advise in that respect of the photonic systems. Data telecommunications, we've got quite a few in the core area. You can pick any 4 of them. And then there's 2 optional ones on the right. So there's stuff in there like future network architectures where the current internet is running on IPv6 and IPv4. But when you do stuff like interspace, if you want to talk to something on Mars, there's a ship going to Mars, TCP IP breaks down totally, and you've got to come up with new protocols. So you just something like store and forward, where you store packets and send them on without getting acknowledgements. So interesting stuff like that. Network stack implementation, that's the full stack. So you have stuff like routing, firewall switching, all that. Network performance, how do you analyze systems? So the whole DevOps space is sort of covered with the DTN major. So people like Google, Facebook, Meta, we call them, IBM, Microsoft, they're all looking for DevOps engineers, and this is sort of very suited to designing the stuff that goes into data centers. Probably the semiconductor, you've got the digital IC design, analog IC design, nano electronics technology, and semiconductor device manufacturing. It's all about lithography and etching and cool stuff like that. If you're into chemistry and physics, that's more up your street, I'm sure. And then there's optional ones, photonics, DSP, uh, solid state, like solid state electronic devices, and photonic devices. So there is an option if you don't, uh, if you're halfway through the course and you're finding it very tough, there is an option to exit with a lesser or alternate award. So we do have a graduate certificate and we do have a graduate diploma. And the difference between them, you have to take, for the graduate certificate, you take complete four level 9 modules, which are 30 credits at level 9. And then graduate diploma is 8 level 9 modules, which will 60 credits at level 9. And they're level 9 awards. They're highly earned and very useful. So don't feel that if you don't achieve well in some subject, it's the end of the road for you. You can resit and get through or not to exit halfway through the program. All lectures are on campus. We do record them usually, but they're not interactive. They're not synchronous delivery, most of them. So it's not the best if you don't attend on campus full time. The lectures are 3 hours each week. So each module will have one 3-hour lecture each week for 12 weeks. They all have continuous assessment. They nearly all have exams. Exams are last week of term. And calendars listed and has all the answers to any questions about when you need to register, when you need to launch an appeal or send. Just on the project then, that's an overview of program 30, but it's same as them. Main body work is done from.
Richard, sorry to interrupt you. We're
Sorry,
just
yeah.
losing your audio a bit there for some
Okay,
reason.
sorry, move it.
It was perfect until now.
Right. 1, 2. Ooh. 1, 2, 1, 2. Yep.
Yeah, that's very clear.
Oh, yeah. Okay now.
Yep.
Great. Thanks, Derek. I need you there as a wingman to check. Um, the fees they're for EU status students. International students need to check fees.ie, DCU.ie. There is some accommodation on campus. You apply and it's randomly distributed, so we can't guarantee on-campus accommodation, unfortunately. But there are websites which will provide lists of accommodation near enough to the campus. Um, um, there is English language requirements, and they're listed on the bottom there. And that's how you actually apply postgraduate admissions. So, just then to give you an overview of what you might expect, as Derek pointed out, this is Dublin City. The airport is up here, and the city centre where all the restaurants and pubs, museums are. It's in the city center. That's about 10 kilometers from the airport. And if you just trace a line down here to this white bit, that's where DCU Glasnevin is. And I'll just bring you in closer. So, sorry if you get dizzy. This is our main campus in Glasnevin. There is a lovely park beside us here, and we recommend that for walks. And there's a nice cafe in the middle of it there. It's tennis courts. Um, so it's important to treat your body as well as your mind when you come to study with us. This is the main entrance. It's on a road called Collins Avenue. And when you come in directly, this is the Stokes building. Um, so all the engineering activities will take place in here or in this building here, which in this picture is only partially completed. It's fully completed now and it's bright red. You can't miss it. Um, Going into the campus, then you might have need to use the library. We'd expect you to use the library. It's quite comprehensive, very useful. They have a lot of stuff online and very good meeting rooms if you want to have study buddies and group meetings. That's very useful. There's also a nice cafe in the front of it, which people miss. It's sort of sunk in there and well worth checking out. Our computing department is next door to us, so there's computing labs in there which are available to you. And further along here, that's our business school. And here's our swimming pool and our swimming pool's in there. And then it's a gym and a exam hall. Here's the accommodation blocks. As I say, they're difficult enough to get, um, but they are on campus, as you can see, right beside the park. One of the main things, we've got a very good comprehensive sort of supermarket there. So if you need anything, snacks or anything, that's the main shop. There is about 9 cafes on the campus, so it's quite easy to get yourself fed. Um, this is the Student Union building, which is a new building that they built, and it's quite funky and lots of open space for study or for taking your lunch. Um, and over here we have the Interfaith Center where you can say your prayers before you do your exams, if you're so inclined. Um, the canteen is hidden in the corner here, and it's quite a huge capacity in there. Cheap enough meals, so you can eat quite comfortably for a reasonable amount. The other place I just want to talk about is this is where international admissions and registry are located. So if you do have issues, anything with visa issues or timetabling, or you need to talk to somebody, they have a help desk there, and you just take a ticket. Usually, people will help you straight away. Um, so that's as far as you go there, DCU. We do have the coast beside us, so it's a half an hour on a bus down to the local beach, which is here. And then if you want to go a bit further, you can go over to Hoth, which is always nice. You can get the train out, and there's a lovely cliff walk where you can see great views of the city. It's completely 13 kilometers, I think, if you do the lot. If you don't want to do the whole lot, you can go halfway and then climb up the mountain, and there's a nice restaurant at the top. But that's just an overview. Uh, as I say, if you need more information, give us an email and we'll be happy to answer your questions, mainly on the academic side of things. Registration, talk to the Global, DCU Global. And that's pretty much it for me. Thank you for your time.
Thanks, Richard. It's great to see the country as well. You certainly situate us. What you will see, actually, I think for international students, just the amount of green that's in the country is surprising, and that comes with weather. In September it does rain. It's green for a reason, the country. So just make sure you check your if you, before you travel over, make sure you check just things like the weather and climate for the country, just so you're prepared for it. It's not bad. We're quite happy. We're going through a heat wave right now at the moment, which is unusual to us. It's in the high 20s, which makes us uncomfortable. Richard, let's say, is that fair? Uh,
This week it's pretty hard
yeah,
going, but
yeah,
when you talk about weather, you do have a lot of solar panels on your house, so we do get sun for pretty
yeah,
much
yeah.
sufficient to
Most of the
heat your
year,
house.
yeah. We get good over the year. The weather is quite good. It doesn't really get very cold. It doesn't really get very hot. So it's typically in the region of 0 degrees on cold days to 20 degrees on warm days. So it's very mild climate. So anyway, just in case you're coming internationally, just that you're prepared for that as well. So I think we should sign off, Richard. This session is a closed session, so we don't have students asking questions. But both Richard and I are able to. It's easy just to Google us, Derek.Malloy at DCRE or Richard.Bulger at DCRE. We're happy to take any questions that you have. So we'll leave it at that, and I'll stop the recording. Thank you.